move, the pile wants to move with it, and then after a while the soil will move, the pile will stay the same. Right? Okay? So this is what it shows. That as the ground moves, the pile will move as well, the close pile. Then the soil keeps on moving, the pile doesn't move. Yeah? But the interesting thing is that when you put the vertical load, you see a certain point, suddenly there is a jump. And that is the instability, that is the period effect. So, in this case P is 0, so no vertical load. But when you put a vertical load, you will see that this movement is increasing, and at a certain point you will jump, and that is the instability. Yeah? Any question this side? And then what happens as this moves, the epidermal moment increases, you get a bending moment exceeding the capacity, you get plastic hinge formation. Right? And you get the plastic hinge will form, pile will fail. Okay? Right. Here is something bit more, just to show that how to differentiate bending failure, buckling failure, and bending buckling failure. Here is some sort of distinction. If bending moment exceeds MB, it's bending failure. So here are some things, but it's just for your future reference. You don't need it now. And another interesting thing, and another interesting point is, so when soil liquefies, say soil liquefied, right? What it means? That means that the particles are not in contact, right? But there's still that soil and the water, everything is there. What happens if you push a pile through the liquefied soil? What will happen? It will eventually lock, and it will start to give you resistance, right? So therefore, if you completely ignore the springs, and if you do analysis, you will get you will get a very large movement, right? Because if you actually that there is water, right? So therefore, so what it is, in a normal condition, the springs look like that form, but when it liquefies, the spring takes this sort of shape. So that's the point where you have a no resistance, right? This is a very, very advanced analysis. So this is 2017 articles. So you can just basically remind, the code will take a few years to bring into account all these things, update all these things. So these are just to remember, if you can get a project to work on this thing, I think actually I will use the updated research. Yeah. So this point is, if the pile is cutting to liquefied soil, right? So at a certain movement, we start to see that it is also giving resistance. At that point, the liquefied soil gets locked in and giving resistance. Yeah? So when you do a model, first thing is find out to what depth it will liquefy. Give a PY springs for non-liquefied soil and liquefied spring for liquefied soil, and run the analysis. Put the vertical load there and the lateral load there. The lateral load will come from response spectrum method, right? And vertical load will come from the vertical load of building. Yeah? Yes.
The displacement isn't continuous. Like, obviously there's less displacement at the bottom than there is at the top. So you'd have more of that load at the top resisting that movement than you would at the bottom.
Yeah, okay, so purely like this is purely a column. You have some springs attached to it, right? So these springs are modeling the pile solid interaction. So this spring is very stiff. When you apply the load, so this thing will move more, this thing will move more, this thing will move less. Yeah? Now as it moves, it then generates some resistance. So this lateral load has to be balanced by these forces. So what the program does, or what this balance does, is try to find out a compatibility of displacement and loads. Yeah? And you typically can use SAP or any program to do these surveys. It's hard to do by hand. In hand, you would do by simplified way to just see order of magnitude calculations. Yeah? Is there any question? Questions so far? This is going a bit. No, it's not. The top one, yeah? Okay, say you have a pile here and this is liquefied. This part is liquefied there, this is liquefied. Liquefied means what? Liquefied means that the particles are not in contact. But now if the pile starts to deform, what will happen? Those particles will then gradually come closer and then it forms a but it needs certain movement. This is that. This is no resistance zone. Then
It needs more display than the other.
yeah.
The profile, is it, do you get quite a lot of resistance or not much? I mean, there's no like reference to how much
Oh,
load.
yeah, I can give you a reference how to calculate all these things. Yeah. So effectively, what happens? So you can basically shift this side.
Okay.
So you can basically shift this and you can get a more or less similar. So if you can shift this, you can get this done.
What are the opposite springs? Opposite springs.
Okay. So this is the settlement. So these springs represent the actual behavior. So we apply the load there. How much will the pile top move? That depends on the friction. Yeah.
So the pile might also get inside, so further inside. What's it made?
Like a nail, yeah. That's the also the force work. So that Juan Pablo Bridge, what happened? It moved down. We have a liquefiable layer. So those springs, that layer liquefied, those springs reaction. Yeah. Now, here are the different approaches one can use to find out those springs, but you can leave it for reference. Here is a sort of just the importance of the shape. Now, it is important to have a correct shape because if the shape is like this, the spring shape, what it means that for small energy vibration, you have some stiffness there. But here you don't, right? So shape is very important of this spring approach, right? And you're asking about some example. Here's an example of a liquefied soil and non-liquefied soil. Say the spring, say a typical spring is say 12 meter depth, right? At 12 meter depth, if the pile moves at that depth by say 0.02 meter, you mobilize so much of resistance. But when it liquefies at 12 meter depth for up to 0.01, there's nothing. Then it starts to build up. Yeah? Okay, this part, next part, I would only give you some important sort of things like this thing is if you look into the whole building, what you can see is before liquefaction you have a very stiff ground, and that's why the building period etc. doesn't consider the foundation. But when soil liquefied, you suddenly see a drop in stiffness because this now acts as a long unsupported column and the length is long, isn't it? That means, do you know how to calculate the column stiffness? Do you know how to calculate the stiffness of a column like this? This 6 EI by L square, yeah, and this is 6 square, right, by L cubed. So as L increases, you start to drop stiffness. That's why you see a very big drop, because L is quite large. Because if a column, so what happens? Typically, you have a column, and the column forms piles, isn't it? So you have a column comes into a pile cap, and from pile cap you get piles. So you can see that there's a very big drop in stiffness, right? And if you have a change in stiffness, this becomes a vulnerable zone of a building. Yeah? And how does, in another sense, what happens is liquefied soil, damping is very important. If you look at the response, what we get response, a structure in an earthquake, damping plays an important role. That's a C term. You have a mass term, K term, C term. Now, if C is high, damping is high, what do you get? Damping is high, you get lower response. Yeah? So therefore, when damping is low, you get a curve like that. But when damping is high, you get lower curve. So therefore, when it's liquefied, damping goes up as well. So you can also get a bit of a lower thing. So when damping for liquefied soil can be as high as 20% damping. Because the whole soil, because the pine has to move in that solid suspension, the liquefied soil and the water, right? So you can also get a higher damping. Okay, this should be adequate for your sort of overall foundation design and yeah. So the important thing is to depth of liquefaction. Once you get the depth of liquefaction, then you can think about the different scenarios of failure, and you have to show how things work. Is there any question so far? Any questions? Structures, what have you done?
And it's
What do you cost?
330.
Stefan did. So Stefan did.
Yeah, I got the email. Up there, imagine. Yeah.
So Stefan, eigenvalue, eigenvector, yeah? And
All that's having that's quite
what is the rate?
Response spectrum.
Cost spectrum.
a
Okay. And that's it. So you need the eigenvalue, eigenvector for what reason? Find the frequency. So basically, if you see everything what we do, we start with T1 and T2. That's the time period, and those will show you how to calculate those T1 and T2. Right? So the mass matrix, K matrix, yeah. And then you did response spectrum, and that will tell you how to get the inertial loads on structures.
But this one, the other here is the frequency of the soil.
No, that is not. Okay, so next few slides you can ignore. I will come down to now these cases just to help you with the coursework a bit. So let's look into Schwab bridge. Again, the Schwab bridge is the middle of the bridge failed. This is not the only bridge where the middle failed. There are other bridges as well. You can see the middle failed, right? There are other examples. There are other examples as well. And it's everywhere. Like if you look into any country, the same issue. And just to give it, put it in perspective, so this is how the layer liquefied. This gray area, right? And this was, you can see the seating length. So this part was on roller, this was on hinge. Now, why will only this middle part fail of the bridge? Any idea why the only middle will fail?
Here's the number.
Here's the number. Yes. So the reason is here. So what you can see, typically we will drive pipe to same length, to same sort of length, right? And as you go towards the bridge middle, you will see that you get slightly unsupported, higher unsupported length in the middle. When ground liquefies, it liquefies to a certain depth. So the middle part has got more unsupported length. It then becomes more flexible. So it deforms more. As it deforms more, the depth falls. Right? That can be an explanation of the thing. Again, we have given this article to read. And here there are simple examples how you can calculate the bridge period, also given in the paper as well. And so this graph is interesting to show that actually, so T post and T pre stands for time period post liquefaction, time period pre liquefaction. Right? So here's the ratio. Right? So the time period, if the time period increases more, you get a more displacement at the top. So SD by SD is spectral displacement, post by pre. So you can see this is not linear, but it starts to curve out. Right? So that means if the time period increases more, you start to get a bit more nonlinear behavior. And this explains why the middle of the bridge fails. Yeah? another interesting example is, if you have a large diameter, you don't see these issues. If the diameter gets, so just to bring you back, now that particular bridge, what you can see is there quite a large depth, long span, and a very stiff foundation.
And therefore just collapses.
So those foundations were very, very large. And if you have a big foundation, the time period doesn't increase. Okay. And to give you an example is here, the bridge that failed and the bridge didn't fail, only difference is as soil liquefies, this bridge time period didn't change at all. It's so rigid. And the other bridge, the time period kept on increasing. Right? If you make the time period increase high during the earthquake, you end up having different issues. Okay. So this will explain why those three bridges fell in the middle. And if you look at this Juan Pablo Bridge, big foundation, yeah? Foundation is big, isn't it? Compared to older ones. So I've given you enough hints about this course. Yeah?
Do you have any problem?
No. Massive foundations. Okay? So if it is, then we can stop here. Is there any question you want to ask? Happy to. Is there any questions? Yes. What you can do, you can make the you can have a single pipe. You can set
With a combination of
you can have 4 pipes. You can just bring a single stiffness. So you can act. You get 4. You can do ER square plus I is the height of E plus or you can say everything one.
Okay, so what in your head, what's the time tomorrow?
Foods is priority.
Nine.
I'm going to do
He doesn't care.
Everyone's going.
Yes, I want to see more.
Wow.
But like,
She doesn't want to see my breath.
I don't know.
Jumping is a very
I don't mind that. I'll be there for that one. Yeah, I'm going to I'll be back. Weekends are good.
I just downloaded that one.
He's driving.
Yeah, exactly. To be fair, I only said I want 50% car. I do, at the moment, I was just 20. Yeah, the back. That's the thing, it's very easy to sort of go over certain macros without really realising. Do you have the pro one, the premium? No, shoots on me. And I've only done like 2,000 rounds today. Really? Yeah. I walked to the gym. No, I just go to the gym. Try and see. Go there. And that's it. It's a bit like.
That's my problem.
Low budget.
Honestly, no one dare get value.
It's denser though,
I know, so but it's not the one in my head, it's the one in my head, so which is quite cool. But I'm a little bit. Oh, mine too. I've got dark clothes, so you know, going on to things. Yeah, I want to do it. We do it in an hour and an hour and a half. Because I know that guy can't join other guys. After six. The thing is, I don't want to do it because it's late. So I can, like, latest is like 7 hours. So I can, like, be there for an hour. Would not be a good idea. Say, like, I have to go to stay. Oh yes, a bit busy. I know.
Doesn't count. I usually do that.
Yeah, I'm alright.
I'm not stressed.
I'm
Yeah, I know.
assuming
I wasn't there.
I haven't studied at home. What about you?
Yes, as well. I've seen you meanwhile. Where were you? You're sleeping.
I know, I feel so bad.
Stefani was very rude.
I felt so bad.
Okay, next time.
On Mondays, he's here for
Oh, really? Yeah, we were saying, maybe we're working out.
Monday, oh yeah.
next year.
Score more drinking.
Hey, your phone.
Oh, gosh, yeah. Thank you.
And other thing is, this one comes down here. Then you get a higher x1.
When it's
liquefied. Then you have x1, x1, then you do x1, plus L1.
And then you just rearrange the name of the light. So you just equate the lever on the pile.
Yeah,
the lever
yeah,
on
but
the
in reality, it would be different. In reality, just explain the whole method.
Yeah.
The force will change.
When you've got this horizontal force for the response spectrum, how does that, so this is on plan with these different piles, so that force is coming this way, and let's say you've got piles like this, how does that force get distributed between these? Is it all equal? Or is it based
No, it's
on-
like you remember the rebate formula we use? You know the rebate formula.
oh yeah.
Yeah, remember?
Oh, in still.
Yeah. We have your main point and you have a movement there, you know. So it's the same thing, you know. Similar way.
Yeah.
You have multiple, it's basically force,
Yeah.
and you do the
Based
pattern
on-
movement and that.
And then.
The main thing is understand how the forces are coming. That's the most
Yeah.
important one. How the force is coming, earthquake force, what does. So then it's building.
Yeah.
Once you know the what
Yeah.
what she does, inertia does.
Okay. And then on this part here, when you were saying the factors, you worked out the factor of safety at 1.84.
Yeah.
How can it still fail then if there's like still
Because they assume the wrong mechanism.
So the
So say for example the bridge is designed is governed by Buckley mechanism, but you check only is bending mechanism.
yeah, and they get 1.84 for bending.
But Buckley is
0.9.
0.8 or something like that. I checked it. In the paper it's there.
Ah, okay.
So because bending it is safe,
Yeah.
Buckley is unsafe. But they didn't consider the code doesn't say checking is there.
Okay.
Otherwise why will have smaller
Yeah.
water?
Yeah.
If it liquefies, then the Buckley will mechanism will
The
be
effective energy increases and the critical buckling load decreases a lot.
Do you know the theory by whom? Who gave this theory about Buckley?
Oil.
Euler gave the Buckley theory, but for why?
Is it? Oh.
So that's my
Is that one?
that's my theory.
Okay. 2004. Okay.
Yeah. So all the papers theory was let's see. That's right. So basically we found out this.
Yeah. To account for that mechanism. Which mechanism is it? The buckling of the Yeah.
Add more miles.
Yeah.
So have a lower soil.
Yeah.
Or trying to have the ground.
Could you potentially tie them all together?
Yes, we are
So then-
the other way, yes,
Yeah.
the market other ways to have the ground improve. So that it will improve that depth.
Yeah.
That expensive, very expensive.
Yeah.
And money will use there when you earthquake comes every 50, 60 lucky.
How do you balance the amount of money you put into making safe design with the probability of it occurring? Because obviously in practice it's going to be down to the client with the money, and they're going to probably more often than not take the risk and say no, I'm not spending money. So what do you do in that situation?
Who's paying you to do for that?
Yeah.
Do what they say.
Yeah.
But then insurance.
Yeah.
Who is insurance? But very interesting area. Very interesting.
Yeah. There you go. So it's only recently that people, since you did your PhD, that people start considering buckling due to the situation of liquefying soil.
Because they study this one, they don't care about structure.
Yeah.
This is a structural concept.
Yeah.
That's the fact that so only structure. This is a everything comes in.
Yeah. But would the liquefaction side is geotechnics, but then the buckling of the piles with the small structures, so those
But then who did the points?
yeah.
So their capacity is the same defense.
Okay.
So they don't know the whole picture.
Yeah.
Why is the failure? So if you look into the building is fine. It's keep it calm, everything is fine. It's not a problem.
Yeah.
So the interface problem.
So wouldn't that be purely down to the pile contractor, the people designing the piles? It'd be their responsibility for them to check this.
Yes, but how will they liquefaction is happening? This is not how the profession works.
Yeah. But would as part of maybe like a design matrix and the responsibility of people's design responsibilities, would it not be part of the?
It should be.
And now it should. Maybe that's what
That's
starts to
now. We have been analyzed.
Yeah.
Put in textbooks. Put in textbooks. But it takes time. It doesn't happen.
Okay. Thank you. Thanks.
Do you mind switching off the camera, please?
Sure.
So I record the lecture in case somebody can come, they can actually get. So altogether you had how many RP lectures?
What was that, sorry?
Altogether you had how many RP lectures altogether?
This is the 6th one now. That's it.
6 one, isn't it?
Yeah.
So I did 3, Stefan did 3.
Yeah.